Imagine tiny particles, just nanometers across, following a program to accomplish exactly what we want them to. We've all thought of what the future may look like, and above all, the magical technologies that would come with it. At the core of many such technologies is the ability to structure stuff at ever smaller length scales. Atomic control. Atomic machines. It's not a single invention in the usual sense, rather, it's something that would inevitably lead to a plethora of technological advancements. The mother of all inventions. The ability to move individual atoms, manipulating them to create structures that nature never made, well, that is possible. Remember those movies where individual atoms are moved exactly where we want them to? A stop motion animation? Well, that is possible. We can move atoms. The technology that allowed that to happen was the scanning tunneling microscope. The way it works is kind of astonishing because it uses an intrinsically quantum mechanical phenomena to image atoms, to move atoms, one at a time. Suppose you have a bunch of atoms that you want to image. How would you go about seeing them? Well, the STM used a probe to scan through the material. The probe at the very edge is a lot of times just a single atom. You give some voltage to the probe, and now as the probe moves very close to the atoms, and by that I mean very close, the current to the probe changes. By measuring it, you essentially scan the position of atoms. This method can also be utilized to then move individual atoms by fine-tuning the properties of the tip of the probe. Now, this could not have happened in a classical world. Quantum mechanics allow particles the ability to jump potential barriers even when they don't have the energy to do it, in a process called quantum tunneling. Normally, the electrons in the probe are bound by the atom to which they are part of. However, the fact that there is a small chance that the electrons may cross the potential barrier of the atom to which they are part of allows the scanning tunneling microscope to work. Why is any of that important? Well, because then we get to see these movies where atoms are at the center stage. This technology was developed by two IBM researchers, Gerd Binnig and Heinrich Rohrer, for which they got the 1986 Nobel Prize in physics. The movie by itself is not the main point here. The main point is the demonstration of the principle. We can manipulate atoms, and with that ability, the possibilities of what's possible changes. In his 1959 lecture titled "There's Plenty of Room at the Bottom," Richard Feynman talked about the possibility of tiny machines. Consider tiny robots guided from outside to perform specific actions that could eradicate certain diseases or enhance human capabilities, or even structuring material at the smallest of scales to give them special properties. In this video, we'll talk about two broad ways in which atomic control may lead to enormous advancements. First would be its application to metamaterials, to form materials with specific properties that are never found in nature, and the other is how it could change computing forever. But remember, the applications of atomic control are far exceeds whatever we're going to talk about in this video, and this is just probably some of the things that are being worked on right now, and the future is just as elusive as you can think. The most popular prospect of metamaterials is to make things invisible. Normal materials can't do that, as you might have noticed. To accomplish such a magical task, we have to engineer materials at the smallest of scales, metamaterials. The definition of metamaterial is kind of vague, and so let's just not get into it, but rather think of it as a completely radical way of coming up with materials with properties that are nowhere found in nature. Invisibility is often depicted as a superpower. In the Harry Potter universe, Harry gets this cloak of invisibility that makes anyone inside of it to be invisible to the outside world. Now, even though the Harry Potter books don't mention what exact material this cloak was made of, theoretically it is very much possible to construct a cloak that could make you invisible. Essentially, what we need is something that makes light move around the object and not pass through it. Normal materials that allow light to pass through have a positive refractive index. However, to attain invisibility, we need a negative refractive index, which sounds absurd, and for good reason. I mean, what does a negative refractive index even mean? A material with a positive refractive index bends light towards the normal, but importantly, on the other side of the normal. With a negative refractive index, light bends such that the refracted light is on the same side of the normal, something that could allow light to move around instead of passing through. It was Viktor Veselago who in 1967 first saw the possibility of such exotic mediums. He found that a medium with a negative permittivity and permeability would lead to a negative refractive index. However, it wasn't until the early 2000s that it was observed for microwaves. Now, this is where the idea of atomic machines kick in. Turns out, to have a negative refractive index for a particular wavelength of light, you need to be able to structure stuff at length scales that are smaller than the wavelength of light that you want yourself to be invisible to. It was therefore easier to attain that for microwaves with their longer wavelengths. In recent times, it has also been done for certain wavelengths of the optical spectrum, for instance red. However, these are only done in very controlled lab environments, not to mention only for a certain wavelength. And as you might have noticed, the world around us isn't just single wavelength. For complete optical invisibility, we would need a lot more control over the atomic structure of the materials. Atomic control. Atomic machines. We don't know how much longer it would take to attain that level of control. However, at least in principle, the cloak of invisibility is very much in our reach, only because of tiny machines. But this is not the only way. If you think about it, instead of bending the light around the object, what we can do is to project the light from behind forward, like holography. You take in all the information from behind you and you project it forward. It would be as if nothing really happened. However, it would be a lot complicated with all the different angles and perspectives, not to mention the energy requirements. The other thing about energy is computation, and so now we're transitioning to the second thing that I wanted to talk about. The world runs on electrons passing through tiny silicon transistors, small switches that encode the ones and zeros that run the world. The computing needs of the world have been on a consistent rise, and they are now more than ever. Especially after the breakthrough of AI, the number of computations and hence the energy required to do those computations is quite significant. So what can be done about it? Well, one aspect of it is to transition to a much more sustainable sources of energy, for which atomic control again would be quite revolutionary in terms of how efficient energy generation is. We are already seeing this trend. Renewable sources are becoming more and more efficient. The cost of switching to renewable sources is declining, which is good for the planet. The other aspect is to engineer stuff so that we can use energy more efficiently. And this is where a new way of doing computation comes into play, by using light instead of electrons, something known as optical computing. For certain kind of very niche computations, such as matrix multiplication, which is heavily used in LLMs, optical systems can potentially be much more efficient and faster. Mainly because when we use light, we avoid a lot of resistive losses that lead to heat, slowing down the system. Also, light doesn't interact as much with other light compared to electrons, potentially allowing for a larger extent of parallel computation. So why hasn't optical taken over the world yet? Well, because there are technically a lot of problems with optical computing as it stands today. The biggest one is of scale. In the current world, individual transistors are as small as a couple of nanometers, which makes our smallest of devices so smart. The way we make them is itself an engineering marvel. It's called photolithography, where we use lasers to carve structures on a silicon wafer, and on top of that, layers and layers of components, creating the tiniest of switches. Nanometer sized transistors. Most light, when compared to it, is gigantic, which limits the size of the components that make up the circuit. Why can't we use light with a smaller wavelength? Well, that has a lot more energy and is not nearly as manageable. The solution might be an atomic level control, controlling the precise way light and matter interact, which may allow optical computers to be much more feasible again for a certain niche sets of use cases. And it would have sounded a lot like how we talk about quantum computers, that they can theoretically be much more powerful for certain kinds of problems, not for everything. The problem with quantum computers is again of scale, but also with the very monitored conditions required for it. These novel computing methods aren't there to replace existing ones, but rather to complement them. Electronics has been revolutionary in its applications, and they're not going anywhere anytime soon. Or are they? The current computing power has been following this empirical law known as Moore's law, where the computing power roughly doubles every 18 months, and it has been continuing ever since 1960s. We've been able to make transistors smaller and smaller, But how long could we do that? I mean, there would come a point when quantum effects would not allow transistors to work the way they currently do. We already talked about quantum tunneling. Below certain length scales, electrons would just tunnel through the transistors. It may feel like quantum computers that use literal particles as bits of information would not be susceptible to such an issue. But then, it's not just the qubits, it's also the supporting infra that needs to be miniaturized. Keeping a temperature on scales of millikelvins and avoiding external environment that affect the system, getting the results out of the qubit interactions, that is a true determining factor of how small quantum computers could be. Once we could arrange materials on the atomic scale, the energy generation and transformation would become highly efficient. The only stuff holding us back would be the fundamental laws of physics, specifically thermodynamics and entropy. Think again of the tiny particles on a scale of nanometers following a program to accomplish exactly what we want them to. Not only an invisibility cloak, but we can build stuff that could turn invisible at will. That could be some scary technologies. We already know how the sci-fi future shows up the technologies of the future. Take the nanotech suit of Feynman. Brilliant. So yeah, the future is atomic. And atomic machines don't just give us invisibility cloaks or faster computers. Rather, they give us something far more powerful. Control over matter and light itself. And once we control matter and light, almost every technology becomes possible. Thanks for watching.